Welcome to homework.
Hello everyone, today we're doing chapter 14, problem 46. And this problem asks us to label the signals due to the proton labeled A, B, and C in this following molecule and correspond them to where they fall in this NMR spectra. And they also asked us to draw a splitting diagram for the absorption due to HA proton. So let's first determine, so here we see that we have 1, 2, 3 chemically distinct protons that all give us some unique splitting patterns. So let's determine which one of these values determine to one of these 3 protons. So the best way to do about that is determine the J value, so the coupling constant. So we know that a larger J value means that there's going to be a larger gap in between peaks. So if I'm trying to find which one is 18 hertz, then I need to determine which one has the largest gap. So I know that we want to determine, for example, which one is 5.7, 6.2, 6.6. We got to determine, okay, so we have a larger gap between these two peaks. Then we have a small gap between these ones and a little bit larger one between these ones. So we can say that these two gaps are the one value, and then we have another value, which is this middle one. But what about for here? Well, for here we have a doublet of doublets. So these two doublets are separated by a gap like this, and then the two peaks that make up each doublet are separated by a very small gap, which are the same. And then this one is actually separated by a little bit larger. These two doublets are separated by a little bit larger than the 6.2 one, and then also, once again, the peaks of each doublet is also a little bit larger J value than these ones in 6.2. So if we're trying to figure out, for example, let's start with the left one, 6.6. So we know that out of any of these 3 peaks, we have the largest space or the largest J constant between these 2 doublets of doublets. So this will be AC, will give us 18 hertz. And we also know that we would have a good amount of space in between the 2 peaks, which make up each doublet. So this we can say is going to be the BC peak. So the same thing, the same letter in each one of these is C. So we know that this must be the HC proton. And then we can double check because the HC proton assists to this very electronegative electron withdrawing group right here. So we know that, yeah, because it cis, a lot of that electron density around the nucleus of HC is going to be pulled off of it, making it go through resonance at a more downfield value over here. So now if we do for the middle one, well, we know that this middle one has a smaller gap in between these 2 doublets of doublets. So we know that's going to be the 11.8. So that is A, B. And then we also know that we have, once again, a very small gap in between each peak that make up the doublet. So that's going to be the 0.9. That's going to be BC. And here, the constants in between these two is B. So we know that this is the HB proton, leaving us here with the HA proton, and we can double check that. So we have 2 very large gaps. So we have the 18 and 11 kilohertz, or just hertz, sorry. So we have AB and AC coupling, J constant coupling constant values. And once again, we can determine here that A in this case is the constant. So this is going to be the HA proton. So now to determine your splitting pattern for the HA proton, well, we know that we're interested in this proton here, and this proton has a neighboring HB, which is chemically unique. So it's 1 plus 1, so we'll have 2, so it'll be a doublet. But at the same time, off the same carbon as HB, we have a new unique carbon called HC. This is chemically distinct from HB because HC is cis to this cyano group, while HB is trans. So we know that HC is unique. So this would also produce a neighboring proton of 1, so 1 plus 1 equals 2. So we get another doublet. So we would have a doublet of doublets. And now for the coupling constant values between them, well, the AC coupling value is 18, so that's going to be a very large coupling value, while the AB value, coupling constant is 11.8. So we know that when we want to draw our splitting pattern, we're going to see some sort of doublet of doublets. So we're going to see a doublet of doublet that's going to be separated. That's going to be separated by a space equal to JAB, which equals 11.8 hertz. And now we know that our HA is also split by another style of proton, which is what we're going to call the larger coupling constant, JAC, and we know that gap is going to be quite a bit larger, being 18 hertz, and this is true. This gap is bigger than this one, so that's how we knew which one to write first. And now we know that this produces the peaks for one proton, which we are calling HA. So this is a splitting pattern for the proton HA using these coupling constants provided in the question stem.